All right. So hopefully you can see my screen and hear me okay. Kia ora and a very early good morning from New Zealand. I wish I could be there to present in person, but I'm very appreciative to all the folks who organized CogSci this year for making sure that folks such as myself are able to present remotely. So big thank you. I'm going to be presenting some work with Laura Germain and Joshua Hartshorn looking at the development of cognitive control over the lifespan. And when I use this term cognitive control, I'm referring to a person's ability to bring their ongoing thoughts and actions into alignment with their current goals and context. And this capacity has been linked to all sorts of important outcomes. And so it has implications for things like education and school readiness, early math and reading ability, the criminal justice system and issues around recidivism, and also healthcare. Lots of different examples you could give here, but this citation is looking at age-related changes in cognitive control and the extent to which people are adhering to their medication schedules. So it's a really important topic that we understand and know more about how it develops across the lifespan. When we go to measure cognitive control across the lifespan, we often use congruency tasks such as the Simon task, the Stroop task, or the Erickson-Flanker task. And all of these tasks have a certain commonality. They have congruent trials in which your automatic or prepotent response is accurate, and incongruent trials in which that automatic or prepotent response is the inappropriate response that you have to override. And the notion is that those incongruent trials are going to engage cognitive control more. So if we take a standard kind of approach, the notion is you give a bunch of participants at different points in development these kinds of congruency tasks. You compute a congruency effect by, for example, subtracting response times on congruent trials from incongruent trials, and then you plot that across the lifespan and see the shape of that trajectory. We often invert that to look at the development of cognitive control. So the notion is that as the congruency effect goes down, cognitive control performance is increasing. And so we call this the inverted U-shaped trajectory. And the notion is that this captures, generally speaking, the development of cognitive control. And while it might be the case that this characterization captures general trends around the development of cognitive control, there are a lot of details that remain unclear. So what I want to do is just step through some of those unclear details. One is when exactly peak performance is observed. So this question is still open because a lot of the developmental work that's done uses a coarse-grained approach where it's looking at a small handful of age groups. So this is an excellent study by Gathar Cole and colleagues. It has a large sample size of more than 500 participants in 7 different age groups, investigating the development of cognitive control in the Simon task. And they found that peak performance was observed at the 25-year-old age group. Now, like I said, this is a really great task, but the problem here is that if you want to identify the peak, all we know is that peak performance is somewhere between 15 and 67. If they had a 21-year-old age group, we might have seen it at 21 years of age. If they had a 41-year-old age group, we might have seen it at 41 years of age. And so that's an important question, trying to identify what the peak in development is. It's also important to better characterize the nature of cognitive decline. So how does cognitive control change with aging? And we have that same issue that a lot of the studies use a kind of coarse-grained approach. And that makes it difficult to know exactly what the shape of that trajectory is. But we also have a big issue with discrepant findings. So a lot of studies have revealed age-related declines in cognitive control using these kinds of congruency tasks, but not all studies have. Some studies have failed to show evidence of age-related decline, including this very large-scale study by LaPlume and colleagues that featured over 40,000 participants between 18 and 90 years of age. They assessed cognitive control with the Stroop task and didn't see that kind of age-related decline. And finally, some tasks purport to show age-related improvements in cognitive control across later adulthood. So this is a study by Verissimo and colleagues with more than 700 participants between 58 and 98 years of age. It used the attentional network test, which is similar to the flanker task, and suggested that performance was continuing to improve in those late adulthood stages. They also do a little lit review where they talk about other studies looking at similar tasks with similar age groups, and they show that 8 studies found this age-related decline, 7 found no effect, and 4 found increased cognitive control. So this is all just to highlight that our understanding of that age-related change is a little bit unclear at this stage. Another question that comes up that's related to the previous one is the extent to which the various cognitive control tasks that we're using correlate with one another and follow similar developmental trajectories. So maybe part of the noise from that previous slide is to do with the various tasks that folks are using. A number of issues come up when we're thinking about this question. One has to do with poor split half reliability metrics for many of these tasks. So there's this excellent paper from Draheim and colleagues in 2019 where they talk about this issue. And they note that generally speaking, you want your reliability metrics, your split half reliability to be at 0.8 or above. However, it's very rare in this work for studies to reach that kind of level. So for example, a great study by Waszak and colleagues in the flanker task reported a split half and response times of 0.44. So our reliability metrics are often not as strong as we would like. There's also an issue with poor correlation among congruency effects within the tasks. So Draheim and colleagues talk about some of their own data looking at the Stroop and flanker tasks, and they say that performance typically correlates at approximately 0.10. And so if these tasks are supposedly tapping into the same underlying cognitive capacities, you might expect those correlations to be a little bit higher. So what we're advocating for is a revisiting of the inverted U, questioning whether or not this really does characterize the nature of developmental change. We want to try to shed a little bit of light on these three questions that I've highlighted, and we want to do that by trying to get very large sample sizes with small age bins and data from across multiple different tasks. So the approach that we want to use is this citizen science approach that Josh and Laura have been advocating for a number of years now. They have this excellent website, Test My Brain, that allows users to sign on, give a little bit of demographic information, and then complete various assessments. And this approach has revealed a perhaps surprising amount of heterogeneity in when peak performance is observed across a wide range of tasks. So we want to try to use this same approach to shed light on the nature of cognitive control development. And I think it bears emphasizing that this approach, in addition to generating very large data sets from lots of participants, also produces data that matches in terms of its quality what is observed in the lab. And that might be because folks who are coming to the website have some amount of intrinsic motivation to do these tasks. So we have data from two different studies. One study had participants complete both the Simon and the Stroop test together. Another study had participants complete the flanker task. So in study one, we had more than 9,500 participants. The final sample size ranged from 10 to 80 years of age. And we had participants do these tasks in a counterbalanced order with 4 practice tasks followed by 28 experimental trials. Those 28 experimental trials were split between congruent and incongruent trials. In the flanker task, we had more than 13,000 participants. In that final sample, we had individuals ranging from 10 to 79 years of age. Participants did 8 practice trials and then 96 experimental trials, once again with half being congruent and half being incongruent. This task was a little bit more difficult. The goal of the task is to respond to the target arrow in the center of the screen. The surrounding arrows are called distractors. The distractors were presented 100 milliseconds before the target, so a little bit more distracting. And then the target and the distractor were presented together for 50 milliseconds. In terms of data processing, we excluded from our analyses any trials that featured response times that were slower than 100 milliseconds or over a second. We also log transformed the response time data to improve linearity and also to hopefully improve, to minimize the effects of processing speed. And then finally, we excluded trials in which the same response was generated twice in a row in an effort to minimize these well-known feature integration effects. However, when we did the same analyses that included all of the trials, response repeat and response switch trials, we saw very similar patterns to what I'm about to show you. So first, let's take a look at the split half correlations. So we did 100 random splits per task and per participant so that we could compute how correlated the congruency effects were. We did that for accuracy and for response time. And we saw a quite good score for accuracy in the Simon task at 0.82, a worse score for the Stroop at 0.47, and a kind of middling score there for the flanker at 0.55. However, if we look at the response time split half correlations, they're quite poor, both for the Simon and Stroop and also for the flanker at 0.22. It's a little bit better for the flanker, though. So generally speaking, these metrics are in line with what's been reported in previous developmental studies that report split half correlations, which range from 0.44 to 0.83. So not great metrics across the board, but in keeping with what we've seen in previous work. So next up, I'm going to show you our accuracy results. So the figure on the left here is showing performance in terms of the congruency effect. And the way that we've plotted this is that smaller effects are associated with higher values on this y-axis, and larger effects are associated with lower values. So up means improved cognitive control and down means worse cognitive control. We're plotting that across the age groups here. And then I'm also showing the slope. If the slope is above the 0 line, that indicates that performance is increasing. If it's going below, then it indicates that performance is decreasing. And so when we look at peak performance in the Simon task, we see that peak performance is occurring around 34 years of age, and we're not seeing significant age-related declines past that in accuracy. In the Stroop task, we see that peak performance is a little bit earlier at 26 years of age, and there's a trend, but it's non-significant for age-related declines after that. And then finally, in the flanker task, peak performance is at about 24 years of age, and then we do see significant age-related declines starting at about 39 years of age in our accuracy measure. So next up, I'm going to show you the same thing for response times. And once again, it's important to note that our split half correlations here are quite poor, so I would take this with a sizable pinch of salt. But looking at the Simon data, we see no real significant changes across the lifespan in the size of that congruency effect. With the Stroop, we see something interesting, kind of the inverse of what we saw early on in development and accuracy. So in accuracy, we saw that performance improved until about 26 years of age. But in response times, we're seeing that performance decreased. So the congruency effects were getting larger until about 21 years of age. That might speak to a difference in the Stroop task versus the other tasks, perhaps due to reading speed and the linguistic components that are associated with it, or it might just be a general speed accuracy trade-off effect. And then finally, in the flanker task, we see something similar to the age-related declines we observed in accuracy. So there are significant declines starting around 40 years of age, lasting through until about 69 years of age. So just to kind of put this all together, a general summary here, we do see some variability in when peak performance is observed. We do see variability in the presence or the absence of age-related decline across these tasks, with only the flanker showing the kind of standard inverted U-shaped trajectory. And in terms of previous work, our work with the Stroop task matches up with that large-scale study from LaPlume that I described earlier, who also failed to observe significant age-related declines in the Stroop task. And our data don't quite match up with what Verissimo and colleagues said. So we do see pretty robust age-related declines in the flanker task. Next up, just want to briefly talk about the correlations between the size of the congruency effects observed in the Simon and the Stroop tasks. Since participants did both of those tasks together, we can look at those correlations. So I'm just plotting those correlations for accuracy and response time across the age group. And you'll see that there is somehow a significant but quite small correlation in the size of those accuracy congruency effects. But for response time, no effect and not approaching significance. So conclusions, just to wrap this all up quickly. I think there is a real need to revisit this general notion that cognitive control follows this inverted U-shaped developmental trajectory. We see quite a lot of heterogeneity in the developmental trajectories across these different tasks. And so it might not be appropriate to kind of think about this general characterization without thinking in a little bit more nuance or detail. I think that this work is also important because it builds on previous work that's been criticizing or raising questions about the extent to which these congruency tasks tap into the same underlying cognitive processes. Previous work has mostly looked at like correlations within a particular sample that's a particular age range to show that there's not a strong correlation between the congruency effects. But this is taking a different approach with a developmental lens, showing that these tasks are also showing developmental trajectories that aren't really matching up across the lifespan. And so I think this also underscores the need for more psychometrically rigorous measures that other people have been calling for. And so in summation, I think there's a lot of value to this approach of trying to collect large sample sizes in small age bins, generally speaking, and more specifically to this kind of citizen science initiative of getting people to engage in these tasks to collect these large kinds of data sets. So fundamentally, ours is a message of caution. We think that there's a need to be careful when you're trying to form conclusions by synthesizing results across a wide range of tasks. So big thank you to all the folks that let us test their brain. Once again, a big thank you to everybody who was organizing CogSci 2022. And we've got our data and analysis scripts up on OSF if you want to check those out, and I'm happy to answer any questions that you might have. Thank you.